Good morning, everyone. So first of all, thank you for the invitation to come and speak today. I am going to talk about translating reanalyses of extreme weather events into different climates. And I hope to persuade you that looking back at historical weather events is still very interesting and very useful, and we can learn a lot from them. And I'm also going to hope to persuade you that using our reanalysis systems that we've all built to do novel, exciting experiments can also be a very valuable use of our time. So I'm going to talk about some extreme events, and this photograph of an extreme event in Dublin, in Ireland, we'll come back to a little bit later on, from the year 1903. But as motivation, I would like to show this figure from the latest IPCC 6th Assessment Report, Working Group 1, the summary for policymakers, had this rather important figure, showing a map of the world with different hexagons, different regions represented by each hexagon. And the hexagons are coloured. And the green hexagons are regions of the world where we have an observed increase in heavy rainfall events. So some of the world is coloured green, where we have confidence that heavy rainfall events have increased. There are lots of grey hexagons. And the solid grey hexagons are regions where there's not enough data or not enough academic papers published to make a confident assessment. And so large parts of South America, Africa, and other vulnerable parts of the world are coloured grey. There is not enough data or studies to make a confident assessment. So there are gaps in our knowledge, and I think we can work hard to try and fill in some of those gaps. There's also some regions which are white and grey, mixed hatching, and those are regions where we're not sure about the sign of the trend. And there's also, for every region, some dots below the region's name. So there's mostly one dot in every region, which means low confidence in the attribution of a trend to human activity. There are, I think, just two regions where there's more than one dot. One is Central North America, where there's two dots, which is medium confidence. And there's one region, Northern Europe, where there is high confidence that the trend is due to human activity. So we have a lot of work to do in both understanding observed trends to try and fill in some of these gaps, and also attributing those trends to human activity, with lots of gaps to fill. So focusing on Northern Europe, where I live, and we have lots of data. So this is a slight bias for Northern Europe. Here is a time series of the wettest month of the year for the UK. We have rescued a lot of monthly rainfall data going back to 1836, and so we can create a UK average rainfall time series monthly going back to 1836. And there is a trend in the wettest month of the year, quite a significant trend, that the wettest month of the year has increased. So this is part of that increase in heavy rainfall events. But there's one month that is wetter than any other, and that is October 1903. It is the most extreme month we've experienced in the UK for total rainfall across the country. So that happened a long time ago, 121 and a half years ago. And so that event happened in a colder climate and in a drier climate. And so the question that I'm going to pose today, and we'll come back to, is what would that event look like today? If that same extreme event, same weather patterns that happened in 1903, which caused the wettest month on record, happen again today, we would expect it to be wetter, perhaps. But how much wetter would it be if it happened in a warmer world? And I think that's a very useful question to ask if we're interested in risk of extreme weather and understanding what we need to adapt to today and also in the future. So the vision that I'm going to present is that we should use our reanalysis systems to do more than just reconstruct the past climate. They are brilliant at doing that, but I think we can also use them for much more and do novel experiments, just like we do with our climate models. We do all kinds of crazy experiments with our climate models, and I think we can use our reanalysis systems to also perform interesting experiments which we can learn a lot from. And so particularly, I'm going to pose these two questions today. So how has a warming world already affected individual extreme events? And so that's one question I think we're all interested in. And also, what is a plausible worst case event in a current or future climate? I think these are two really interesting questions that policymakers want to know about. And I think we can help answer those questions by translating reanalyses of observed real weather events that have already happened into a warmer climate. We can also take recent events and translate them into a colder climate and learn about attribution as well. But I won't do that today, but that's where we're going to go next with this piece of work. So what tool are we going to use? We're going to use the 20th century reanalysis built by Gil and Laura and their colleagues. We've heard about it already. It covers the period from 1806 to 2015. You get data every 3 hours with 80 ensemble members. It uses the NOAA weather forecast model at about 75 kilometers. It assimilates only historical surface pressure observations, and that's important. We'll come back to that, using an ensemble-Kalman filter. But that allows us to look at the weather of 1903, when we had that wettest month on record for the UK, as a proof of concept. So we're going to come to the wettest month a little bit later, but the first event I'm going to talk about is another weather event from that same year. And this is a storm known as Storm Ulysses, which hit the UK and Ireland on the 27th of February 1903. And here is the hand-drawn synoptic chart drawn by the Met Office in the UK on the morning after that storm. There's a big low-pressure system over Scotland, northern UK, lots of isobars drawn very tightly together, very strong winds, you would imagine, from that. And so that is the best reconstruction that was available at the time using pen and paper only and the observations. So we've got really good information about this storm. We also have photographs of the damage. So this is the photograph I showed at the beginning from Dublin in Ireland. And this particular photo, the trees have been blown down in Dublin, and the fact that the trees were blown down was mentioned in the famous Irish novel called Ulysses, written by James Joyce. And so this is why the storm is known as Storm Ulysses, because it actually inspired part of that novel. We also have other photographs from other parts from England. So a town called Morecambe on the west coast, the pier was ripped to pieces. And we also have a photograph of a train that was blown over by the wind. So we know the winds were exceptionally strong and caused a lot of damage. Several people lost their lives, lots of shipwrecks. It was a very intense storm. But how intense? So if we go to the 20th century reanalysis and pick out that morning, 20th century reanalysis has a storm in roughly the right place at roughly the right time. Great. But it's nowhere near as intense as was drawn by the Met Office that morning with pen and paper. That's a bit embarrassing. Right? We're using our modern weather forecasting technology, everything we've learnt about the weather and climate system, and we've applied it, and we're not as good as a pen and paper from at the time. Okay? Now, why? Why have we not done as well as the Met Office did on the morning? Is because the only observations that were available to 20th century analysis are the grey dots, and there's not very many. There's one observation in Aberdeen in Scotland at the centre of the storm, which is doing a lot of work. So the answer is that the Met Office had more observations available to them at the time to draw their synoptic chart than we have available to us today. So where are those observations? Those observations are written in very small handwriting on lots of pieces of paper, still stored in the Met Office archives. So a few years ago, we had a project asking volunteers to transcribe these observations from paper to digital. And we transcribed millions of observations from a sheet like this and many other thousands like it. So we now have those observations, but we can't go back and rerun the whole reanalysis with that, but we can just do it for a year. So we've gone back to 1903, we've rerun the reanalysis, adding in these extra observations that we've recovered from the paper. And when we do that, we now have all of the grey dots available to us now, so lots more grey dots. The storm is more intense now when we've rerun the whole reanalysis system. The value of data is clearly huge. The isobars are close together, the winds are stronger, this version of the reanalysis is now plausible. The winds that we see in the reanalysis are strong enough to cause the damage that we see from the photographs. And we only know that because we've rescued those observations. The winds in the original version are not strong enough to cause the damage we see from the photographs. So what does it look like in other respects, this storm? So there's two components here. So the top row shows the wet bulb potential temperature at 850 hectopascals in the original reanalysis on the left and our improved version on the right. And what you can see, even though we've only assimilated extra surface pressure observations the reanalysis has changed at a higher level as well. And now it looks like what we call a Shapiro-Kaiser type cyclone. And these are the types of storm which we know cause strong winds and lots of damage. So it now looks very, very plausible in the improved reanalysis. And the strongest winds happen in the southward edge of the hook shape of the cyclone. And that's where we see the wind footprints in the bottom row. So this is the strongest winds as the storm passed over. And in the original reanalysis, the strongest winds are not in the right place. They're too weak to cause the damage. But in the improved version, the wind footprints where the strongest winds happened where we have the photographs of the damage, and that happens at the right time as well. And so this is a very credible reconstruction, but it's only possible because we've added in those extra observations. And we've compared other aspects of this storm as well, like the rainfall and the storm surge and other aspects, and the improved reanalysis is much better in every regard. So we can also now look at how extreme this storm was. So what we can do, we can take our improved reanalysis and the original version and compare the winds in that version to all other modern events. So we've taken the 20th century reanalysis for the whole of the 1950 to 2015 period and gone, how extreme was 1903 compared to that entire modern period, which is roughly the length of most of our full input reanalyses. And it turns out that in some parts of the UK, this is the strongest event on record. It is stronger than any other event in the modern period. And that has added really valuable information about the risk of extreme winds in this part of the country. So the purple regions are where this storm is stronger than any other event. So there is clearly a very extreme event. We've actually got insurance companies now funding us because they have amazing interest in understanding past events like this, because they recognise that there are events in the past which can add to their understanding about the risk from extreme windstorms in this part of the world. So that's our first experiment that we've run with the system. We've added in these extra observations. We made a very small change to the assimilation scheme as well. I'm not going to talk about that now, but that was our first experiment. Add in the observations, see how that improves things. But we can go back to the reanalysis and do a second experiment. And the second experiment is the same as the first one. We've added in those extra observations, but we've also changed the boundary conditions of the reanalysis. We've warmed up the SSTs by 2 degrees everywhere, uniformly, as a proof of concept. Okay, it's not realistic, but it is. We're going to just hit it really hard and see what happens. Okay, so we have started the experiment during 1902. We've warmed up the SSTs. We've allowed the atmosphere to come into balance with those warmer SSTs. The atmosphere becomes warmer, it becomes more humid, and then we simulate the observations for the whole of 1903 and see what the weather of 1903 looks like in a warmer world. And so we can look at extreme events anywhere in the world in that year with a single experiment. And so we're going to see what that does to the weather experience during 1903, imagining if it was in a much warmer world than occurred at the time. And this is what happens to Storm Ulysses in that simulation. So on the left column, we have the improved reanalysis, experiment number 1. And on the right, we have the warmer world version, experiment number 2. And the top row shows an animation of the wet bulb potential temperature, which I showed earlier, at 850 hectopascals. And so you can see the storm coming across the UK in the warmer world version. Unsurprisingly, it is warmer. But the shape and the structure of the storm is the same. We're simulating the same weather, but in a warmer world. So we're simulating the same storm, but with a warmer atmosphere, a more humid atmosphere. The middle row shows the wind speed at 10 meters and the sea level pressure. And again, as you can see, we see the same storm. The contours of the sea level pressure are basically the same, and the winds actually increase slightly. The strongest winds get stronger in the warmer world version compared to the original version. And the bottom row shows the rainfall every 3 hours as the storm passes over. And even by eye, you can see that the rainfall falling from this storm is more intense in the warmer world than it was in the original world. Okay, so this is a very clear example of how climate change, how a warmer world is affecting an individual extreme event. And the rainfall increase is about 25% over land, so it's not small. Okay, so to summarize some of that, we now have 2 rows here. We have the wind footprint on the top row and the 2-day rainfall during the storm on the bottom row in these 3 different experiments: the original, the improved version, and the warmer world version. And so we can see that the wind footprint gets larger when you improve the reanalysis, and it gets larger again in the warmer world version. Stronger winds, more damage if the storm happened today. And the rainfall as well is better represented in the improved reanalysis, and it gets more intense when you represent that same weather event in a warmer world. But you can also look anywhere in the world, as I said. And so there also happened to be a heat wave in Australia in January 1903. And so we can look at that event as well. And what you see is, unsurprisingly, the heat wave is more intense in this example, where you have warmed up the SSTs. So you're seeing a stronger heat wave in Australia. So again, it's very interesting information. Southwest Australia was exceptionally hot at that time, and it would be even hotter if the same weather pattern happened in this warmer world version. And so this is done by colleagues at the University of Melbourne. So if there are other events anywhere in the world in 1903, please tell me about them, because we can look at them. I'm happy to share the data. But we can do a third experiment as well. So the third experiment is adding extra CO2. So we did not increase CO2 in the first experiment, in experiment number 2, where we warmed up the SSTs. We kept CO2 fixed. In the third experiment, we have increased the SSTs, and we've also increased the carbon dioxide levels to roughly equivalent to what would cause a 2-degree warming. So when we compare that second pair of experiments, we can isolate the effect of just increasing the CO2, irrespective of what it's done to the SSTs. That's a slightly unusual experiment to think about, perhaps. So we can now revisit October 1903, the wettest month ever for the UK. So on the left-hand side, we can see the rainfall during that month in the improved reanalysis, and in the warmer world in the middle, and in the warmer world with extra CO2 on the right. Now, there's not a huge amount of difference between the warmer world and the one with increased CO2, but actually the amount of rain has actually dropped slightly in the warmer world with increased CO2 experiment. And this is physically expected. There's less energy available in the atmosphere for latent heat from precipitation because the CO2 is absorbing the energy instead. So that this is expected, it's well known that we would expect to see the intensity of rainfall drop when you're just adding CO2. And to highlight that more explicitly, if we look across the whole of the UK, across the whole year, and every 3-hour window, we can look at how much the extreme rainfall has increased in these 2 experiments. So in the warmer world version, where we've just changed the SSTs, the intensity of the rainfall has increased by about 20% at the highest, for the highest rainfall amounts, and it's slightly less in the warmer world with extra CO2 experiment. Okay, so the rainfall increases in intensity in a warmer world. The intensity increases are larger for more intense events. That's bad news, I would say. But when you actually do the slightly more realistic experiment, when you're adding the CO2 as well, the changes are slightly reduced. Okay, so we're isolating the information from the 2 different effects. I think that's quite helpful to think about. Okay, so we would love to collaborate and build on this work that we've done already. So we're funded to look at many other historical events that have happened in the past. We're going to look at storms, floods, heat waves, droughts. If you have a particular event which is important to you and your country, is iconic from the past, we would love to know about it, see if we can do these experiments with those events. We want to fill in those gaps in the original IPCC map to talk about what we can learn about changes in extreme events. Because we need to give more information to the parts of the world which are vulnerable to climate change, which were grey in that original hexagon map. So please tell me about your historical events that we should consider. We also plan to extend the 20th century reanalysis. So currently it ends in 2015. We're working with Gil and Laura and others. We're going to have an extended version to go up to now-ish. And we're also going to produce both colder and warmer versions of that period. Okay, and the colder version of that period will be used for event attribution. So we'll be able to explain and come up with an estimate of how all the recent events that have happened in that decade period would have looked like in a colder world. I think that's really valuable communication opportunities to talk about how climate change is affecting every extreme event in that period. And the warmer world version is very useful to think about how those events would look in future if they occurred again. That helps think about risks and how we might adapt to the changes that we expect to see. So it's future storylines of 21st century weather That's the kind of concept that we would like to think about. We're also going to do some work with downscaling and some impact models to explore the changing consequences for these different translated events. We think of any number of different opportunities, I think, health, hydrology, wind damage, wildfires, renewable energy, and the list will go on, I think. So there's lots of opportunities here. Please come and talk to us if you're interested in thinking about any of these aspects. Just to summarize then, so reanalyses are sparse input reanalyses combined with historical data recovery. We can produce very credible simulations of weather extremes, such as a severe windstorm and heavy rainfall events, even if they occurred more than 100 years ago, if you have enough observations. And we can also show that the improved reanalysis that we built better matches independent observations which were not assimilated. So we can also evaluate those improvements as well. I haven't talked about that very much now. And then we're working on translating these events into a warmer world. And this will estimate how the consequences of individual weather events have changed. We're going to fill in these geographical gaps in our understanding of changes to extremes. And we're going to build storylines of plausible worst case events that could occur today or in the future to aid policymakers making real world decisions. And we're going to extend this approach to think about event attribution and try and translate these recent events, which we've seen so many of over the last decade, to go to both cooler and warmer worlds and think about those opportunities that approach offers us. So I think I'm hoping that this has persuaded you that we can do these novel experiments with our reanalysis systems. We can learn a lot and actually answer some really important questions which society has, and we can answer those with reanalyses. Thank you.